Thank you so much, and thanks for the invitation. I was talking to Marisa that I'm always glad to be here. Always happy to be back at UFMG and see some familiar faces and some new faces as well. So I will quickly share some work that I've been doing recently. Let's see if I can share my screen here. All right. So one of the issues that we have that kind of affect the things that we want to do and how we want to train students to use XR is the complexity of developing applications for XR, right? So yesterday in the workshop, we used WebXR, which kind of removes some of the barriers that we have for building interactive applications and deploying them in different devices. And today we have, let's see if I can switch this here. Okay, it's not working. Maybe I should click here. Okay, yeah. So today we have many different applications that allow prototyping for different kind of domains, right? So we have applications for drawing, right? We have applications for CAD, and we have also applications that allow us to build some part of what we need for games. But one of the essential problems is that we want to be able to build interactive applications, and for that we need a little math, right? We need to understand a little bit how to rotate objects, how to combine different objects. I'm having a little trouble here with the screen, but okay. So you can see both the screen and the computer at the same time. Okay. So some of you may have used or may have heard of processing, right? Which is an application that we use a lot in computer science to tell students to get them motivated with programming and doing small interactive applications by doing visuals and generative art and so on. And some of you may have heard of Scratch, which is like also very famous and use something that we call block-based languages to allow us to remove like syntax errors when building those applications and just make things a little bit easier. And some may have heard even about Alice, which brings the same idea but now to a 3D environment. So objects have like positions in 3D space, you can do rotations and so on. Recently, there are some new applications, most of them like research prototypes, that try to do the same thing with VR, right? So the idea is that, okay, if you are building a VR application, can you have a better way to build interactive applications and understanding the relationship between these different objects in there? So this research came up with these two research questions, right? The first one was, what is the impact of VR on students' perceptions of competence in programming, and how does VR impact the performance of 3D programming tasks? So what we want to do is make students more comfortable when dealing with VR applications and building our prototypes. And these prototypes can be from a variety of types, right? Ranging from games to simulations to architecture applications. So I will go to some of the concepts here which are important to understand this work. The first is self-efficacy. So self-efficacy is defined as the beliefs about one's abilities to do actions deemed required for achieving desired objectives. Right? So it's just how much you feel that you're competent enough to do what you need to do. And this is important why? Because it's an important determinant of integrated programming learning, and even then other factors like exactly how good you are in math or how knowledgeable you are about the instructions there. What really affects your ability to continue is how much you believe that you can continue and go on. The other important concept here is spatial abilities, right? Spatial abilities is basically a way that term that we use to describe all the multiple factors that are involved in our capacity to understand and remember, mentally transform visual spatial objects, right? So seeing an object from a different perspective or rotating an object in your mind. Again, this is important because it has been recognized as a critical skill for the success in engineering, science, and visual arts. Okay, so I'm going to talk about Abacus, which is our research prototype. This was developed by one of the master students, Nelly Sam. And the idea is that once you are in VR, you can use block-based language to build new environments from VR itself. So it's like you have control over reality. You can instantiate new objects, you can make them move, you can create conditional statements. This is a video that should play, but probably because we exported the file, it's not playing anymore. So, okay, this is sad. But you can go on my website and be able to see how it works, or I can just quickly explain here. So basically the environment consists of like 3 tabs. One of them is a menu that allows you to access different block components, for example, components for conditional statements, components for loading 3D objects into the scene, or components to do loops, right? And a main tab where you actually do the coding using block-based language. So you just snap the different blocks in order and set their parameters. And in the application that we use for a study, there's also an extra tab that allows you to see a small tutorial with a video of what you're trying to achieve. So our goal was to try to understand, okay, what does VR brings to students which are just learning how to build this sort of application. And a good way to do that is to make a study and where we divide the participants into 2 different groups. So one group we use a PC, a computer with this mouse and keyboard, and another one we use VR, which is this version of Abacus that works inside VR. So the platform or environment here is like between subjects. And we also were interested in seeing, okay, how does this ability to build things in VR affect you in different tasks? So we basically divided the tasks that we need to do or need to know to build these XR applications into 2 categories. One is like procedural tasks, like, for example, if we're writing an algorithm to sort a list of objects, right? They don't involve any kind of 3D spatial manipulation, but allows us to build things in a more abstract term. And we call here math, which is basically understanding of how to use like linear algebra, rotations, and add vectors to achieve what you want to do in space. And just to have show you how the tasks look like, this is an example for the procedural task. We basically ask the students to go from one row of trees to like a forest where we have several different rows of trees, right? So in this case, you just need to build a loop that will instantiate different trees along that plane. And this is an example of a math task. So we have a carousel there, and the goal is to add some horses and make them rotate along with the carousel. Of course, just showing this directly to students can be hard if they never did it. So we do 2 examples before. One example for the procedural task, which we show them how to make a brick wall coming from a single line to several lines. So it has some analogies with the forest task that I showed before. And this other one is an example of how to do a solar system that we just did yesterday in the workshop, where we show them how to make Earth rotating around central sun. So this is the outline of the study. So we have a background survey, and then we have VR questionnaire. We do a self-efficacy questionnaire. Then we do tutorial for task one. Then we do a self-efficacy questionnaire again. Then we do a tutorial for task 2, and then task 2, self-efficacy questionnaire again. Then we did some extra standard questionnaires, user experience, NASA TLX, and then we ended with an interview. To give an idea of what the self-efficacy questionnaire is, we have basically 2 blocks. In the first one, we ask questions such as, I can write a script. This is a Likert scale question. So I can write a script to create one object in 3D environment, or I can write a script to create multiple objects in a 3D environment. And in the second block, we have questions that are more general, like, in general, I'm confident in my ability to program, or I can complete a programming project if I have a lot of time, or I can complete a programming project if I can call someone to show me how to solve the problem first. And we use this to create a score of self-efficacy for the students. I mentioned about spatial abilities, and for measuring that, we use the cube rotation test, which is basically a test that asks you to show if the two cubes are the same or they're different. So you have to see which letters are in which face, and there's a series of questions where you ask when you answer same or different. This is also a video that, oh, this is gonna play. Just show the study environment. So we have their a participant, and here we have vision from the PC where he's doing the task. You can see here there is the tutorial with an example of what they're trying to achieve, and they're just building the blocks to make it work. Because they're in the same environment, they're actually seeing the things being built and modified right in front of their eyes. This is a table that summarizes the different measurements for the participants. So we had participants from 1 year of experience to 13 years of experience. Mental rotation went from -5 to 19. And the time to complete the different tasks ranged from 101 seconds to 1,244 seconds for task 1. And for task 2 was slightly faster, 80 and 119. So this plot shows the distribution for self-efficacy, the initial self-efficacy for VR and for PC environments. On the first column, we have the initial self-efficacy. Here, we have the self-efficacy after the math test, and here the self-efficacy after the procedural task. Okay, so this is the more interesting plot that shows us how self-efficacy changed over time from the initial measurement to the measurement after the first training and after the last training. So on the top row, we have the VR, and the bottom row, we have the PC. Each line is a subject, and each of the 3 points represents one point in time. The baseline, when they arrive, after the first and after the second. So just by looking at it, you can see that there's a lot of increase from the baseline to the first, and basically all the participants had an improvement in self-efficacy over there. And from the first to the second, there is some small increase, but most of the time it's basically stayed the same, right, compared to the increase from the first one. Just as a note, we swapped the 2 tasks between participants. So some did math first and some did procedural first. To understand what's going on, we fitted a linear model on it. Basically, we use mental rotation, experience, and environment as predictors, and we express the output as the ratio between the final self-efficacy and the initial self-efficacy. Yeah, we evaluated different models, and this one was the best one to fit the data that we had. Here's some information about the different coefficients. A significant coefficient for experience, environment, and an interaction between mental rotation and environment. So here are the plots to make it easier to understand. So in the lower, in the x-axis, we have experience. On the y-axis, we have the ratio between final self-efficacy and initial self-efficacy. And each of the lines represent one of the environments. Red is the VR environment, and PC, in blue is the PC environment. So we see that as experience increases, right, the gain of self-efficacy reduces. And as we go from lower experience, we see that the VR environment had a higher gain of self-efficacy compared to the PC environment. This is a similar plot, but showing now mental rotation on the x-axis. Again, red is the VR environment and blue is the PC environment. So we see that participants that have lower values of mental rotation also show the greatest difference between the two. Participants with higher values of mental rotation basically saw no difference between using the VR environment or the PC environment. And again, there we see that participants in the VR environment with low mental rotation abilities also had the highest increase in self-efficacy. So basically, we saw that the behavior of the VR participants is congruent to what we call compensator hypothesis, which basically says that participants with high spatial skills gain less from VR because they don't need the VR support to do the tasks well. So our findings indicate that VR was most effective than PC, right, in raising participant self-efficacy, particularly with participants that have like lower spatial abilities or that have low experience in this type of tasks. And that's it. Thank you. If there's time for questions, I'm here. Otherwise, we can just move on.
So thank you for your presentation, Wallace. I think the questions you're addressing, they are very critical and important. If we take from our background then into computation here in at architecture course, I see a similar parallel of how we came step by step closer to the inner workings of the computer, the codes and algorithms, through this kind of interface that enables us to do coding with building blocks. I remember when I was at school here some 15 years ago, there were enthusiasts that went to AutoCAD and trying some programming, even selling some plugins to the market. But there were a few enthusiasts here. But when there was a moment when in Rhino, the modeling software, someone from inside the company resolved to make a plugin that enabled people to program with building blocks. It became a really huge wave of users changing the way or trying new ways of designing with this idea of parametric design and algorithmic architecture. So it was a big, I wouldn't say a revolution, but something that really changed the way people used or access this code. So I think this idea to bring this to VR, it seems really important to me. So congratulations. And what are the next steps, do you think, in how to build these blocks? Because if we use these blocks on the computer, you have this idea of really a block. But when you're doing this in virtual reality, when you have space, does it change the way you code? Or it is simply a way of connecting? Because when you're connecting two dimensions, it has a sort of overview. Does it really change something when you connect these elements in 3 dimensions? Do you saw something like this in your work?
Yeah, thanks for the comments. So if I understand the question correctly, you're asking about how they use the interface to code? Is that correct? Like,
did you perceive a change in how people code in 3 dimensions during your observations?
okay, but you're not talking about the interface itself, right? You're talking about coding in general.
It's about the interface also, because it has an impact on the interface.
I can comment on both. Yeah. Yeah, for a lot of tasks, when we looked into like translation between like PC to VR, we we keep asking ourselves, right? Like, oh, but why you're doing this in a 2D window if you have the whole space for it, right? And some people have indeed tried to use like what they call like is like blocks, like spatial blocks, right? So node-based programming, like MaxMSP and Blueprint, I guess, where we have different nodes, and instead of adding blocks, you just connect one node to another. So one of the work that I showed in the beginning try to pursue that strategy where you just have blocks with lines. But I think in the end, it's the same argument as typing your text, right? It's symbol based. It's hard to give a reason for making it in 3 dimensions if it's like really a 1 dimension problem, right? So we just stick with the interface that people know how to use, which is like blocks in 2D. It might be interesting to see if there are any gains of spatializing that, but it's hard to say there is one. Maybe someone will find a good way in the future to make it work. But regarding the second question, right, which has to do with the changes, right? So I showed that there's some changes here in self-efficacy, right? So there's something that takes on people when they are in VR environment rather than in PC environment. We can say that some of that is because VR is so cool, right? But the reason for pursuing this exactly type of task, which for chance is useful for us because we do we do VR programming and we are dealing with those questions all the time about rotations in space and so on, is because those tasks rely on your ability to understand what's going on, right? Like yesterday when we were talking about changing the frame of reference of the ship from like this and then rotating like around the planet like this, and that from your perspective inside the ship, it will feel that the Earth is rotating below you, right? That requires some skill, right, and some experience, and that's where I see at least part of the change come from, just for the fact that you are into this space and you don't need to make the translation from the 2D of a computer to the reality of 3D space and knowing, okay, right is on there and I'm facing this way, right? That has a little bit to do with being embodied on that same space of the problem that you're trying to solve. That changes how they approach the problem, right? In a certain way, I believe that's easier for people to understand than having to do this extra translation from 2D to 3D. Yeah.
Thank you.
Thank you, Wallace. I would like to ask a question too. It can sound a little bit silly, but
no, they're no silly questions.
I'm more interested in the composition of the team that made this research, because it has like a super clear steps of methodological procedures, etc. And this is a part that since we work mainly just with architects and designers, this is a part that we like it's not like a super solid ground for us, so we tend to go to more qualitative research all the time because I think we lack some kind of knowing about the procedures you took to make this research. So if you can answer it, please.
Okay, so you're talking about the methodology, right? So why did they approach it in this way? Yeah, so most of this research was done by one master's student in computer science, especially all the technical implementation. At some point in the project, we had help from someone, also from computer science, but had some background in computer science education. And some of the ideas for the initial tasks came from her. At the time, she was a PhD student. So we had some discussions about, okay, yes, if you want to measure this, what would be the best approach for doing it? And as a lot of questions in science and research, right? There's no right way. You just have to try to focus on what are the questions that you're trying to answer and trying to find a design that will minimize like confounds, right? Like in our case, we're trying to figure out, okay, is there any difference from this environment to PC, right? So the the more obvious way to do that was to, okay, let's have some people in the VR and some people in the PC. And there's a lot of studies that do that, right? But even then, there is a decision to be made there, right? So you can try to have the exact same environment in the PC and in VR, which is kind of what we did. We have exactly the same environment. The only difference was that one was 2D. But on the other hand, what you could do is to try to use the best example for each environment, right? So, for example, we use a mouse on the PC because that's what is available, right? A cursor that you can point. So in VR, we use an array that you also point to the menu and use it to select, right? But you could think about other types of interaction that would potentially be easier or more fit to a VR environment, right? Like, I don't know, having a menu in your hand. And we did in fact have that at some point in the project where you have a menu and you just click it like in a palette and you can move it around with you, right? So those are little questions. For example, we also divided it into 2 groups, right? And it's between subject, which means that whoever tried the VR version didn't get to try the PC version and vice versa. That also brings some issues, right? Because for some chance, you may have different people in the VR environment than the ones you have in the PC environment. So you have to make sure that's more or less balanced and there's nothing else that can make the difference that we're seeing here. So most of the time, there's no right answer. You need to just try to do the best. And a good way is just to look at the literature and see what other people have done before and if that fits your problem or not. Yeah. I didn't answer your question, but okay.
No, you did in part. I was interested if you have people from other disciplines working with you, like, for example, people from psychology to validate some kind of questionnaire and etc., or was just people from computation background, etc.?
Yeah, for this one, no. But yeah, I would recommend you have a collaborator in that area if you can. Yeah, like in the project that there's another project that I worked on where like Sarah from architecture was part of the design and helped us to sketch a lot of things just because it brings another view into the subject. So. All right. Thank you so much.